In a past video, I had showed how to find the mechanical advantage between two gears. And I'll do it here between gears A and B. All we have to do is divide the output radius by the input radius. So if gear B is considered the output here, and gear A is the input, the givens say that gear A has a radius of 4, whereas gear B has a radius of 8. So B is twice as big as A. We just want to divide them two and get the mechanical advantage between the two is going to be 2. All right, the next step in the process would be to find the mechanical advantage between gear B and C. And we see that there is a 12:8 ratio. That's a mechanical advantage of 1.5. So what is the new way of finding the overall mechanical advantage? There's an easy trick for it. The total mechanical advantage will simply be a product of the first mechanical advantage times the second mechanical advantage. So all we have to do is plug in the 2 and the 1.5. Multiply to get the total mechanical advantage is 3. And that should make sense for this setup because gear C is 3 times as large as gear A. So that means we're going to magnify the torque. So whatever torque we input into gear A, the torque that gear C feels should be 3 times as large. All right, 1B says, assume the gears are all moving with constant angular velocity, and the force of B's tooth on A's tooth is 10 newtons. What external work gets done on the input gear in a complete revolution? All right, so there's a lot to that. Let's start with just drawing the forces on the teeth. So gear B can push upward on gear A. And by Newton's third law, gear A can push downward on gear B's tooth. The givens say that this is a 10 Newton force. And so by Newton's third law, this has to also be a 10 Newton force. So gear A is pushing on gear B with 10 newtons. Gear B is pushing back on A with 10 newtons. So that brings into question, what must be the external force on A? Should there be one? Well, the answer is yes, there must be. There must be an external force here acting on A because right now A would be accelerating. It would be angularly accelerating counterclockwise if that was the only force on A. So we need to introduce another force from the outside in order to keep A balanced. But we need the torques balanced. So if the force of B on A causes a counterclockwise torque, we need to introduce our own force that would create a clockwise torque. And that force could be supplied by a person, perhaps, just pushing on the tooth, simple as that. They'll push with an external force. Now, how hard do they have to push? Well, hopefully you can see by the symmetry of the situation that in order to get the torques to balance, the forces have to balance too. They have to match in size. One creates a clockwise torque, that's the person, And the resistance force here, the reaction force, creates a counterclockwise torque, and they cancel out. Now A can rotate with constant angular speed. All right. Now if A pushes on B with 10 newtons like that, in order to achieve rotational equilibrium for B, we need another force on B. How big does it have to be? Well, 10 newtons, because we need the torques on B to balance. And so C is applying that 10 newtons on B. But B must also be applying 10 newtons on C. That's Newton's third law. So as you can see in this train, the force that's felt is the same all throughout the gear's teeth. But what isn't the same is the torque. So this one says, what external torque, what external work gets done by the man here on the input gear? So we had looked in a past video, at linear forces and how they can create work if there's a displacement of the object. Here, our gears aren't really going anywhere as a whole. They're staying put, but they are rotating. And so the way that you create work in an angular situation is by the formula work equals torque times delta theta. We have to know how much torque is being exerted on A by the person, and also what angular displacement does A have. So the question asks for how much work is done in a complete revolution. So in a complete revolution, we're going to use a delta theta of 2 pi. We actually have to use radians for this formula involving work. We don't want to use revolutions or degrees here, because if we use radians, we'll actually get joules, which is what we often want. All right, so let's figure out how much torque there is on that gear A due to the person. Well, they're applying 10 newtons of force with a lever arm of 4 meters. So that's going to be 40 Newton meters. All right, so when we go to calculate the work, we just have to do 40 Newton meters times 2 pi. Simple as that. So we'll get 80 pi. And I'll just do that on calculator here. It's about 251 joules. Okay. Now, in the same time that gear A makes a complete revolution, what work does gear B do on gear A? All right, so here's where we want to look closely at the gears and just use a little bit of reasoning here. If one of them goes a full revolution around, and it's in contact with a gear that's twice as big. So this tooth goes all the way around the gear, comes back to where it started. The arc lengths that the teeth travel have to be the same for the gears so that they interlock. So the question is, how far can B's tooth get in that same amount of time? The answer is it won't get all the way around. It'll only get half the way around, so that whatever this distance is here equals this distance here. So if we shade it in to show how much of the gear has actually rotated, it's half of a revolution. So that's my point. If this delta theta is, let's say, 1 rev for A, then for gear B, we ought to see 1/2 rev. And then what if you connect that to an even larger gear C? How much of the gear will rotate? Turns out only 1/3 of it. So the arc length here has to be the same as the others, but see, the circumference for gear C is 3 times as large as gear A. So that means our delta theta of C is 1/3 of a revolution. So let's think about that. The torque increases by a factor of 3. It's 3 times as much torque. But the delta theta is 1/3 of what it was in gear A. And remember that work is a product of torque times delta theta. So if we take our work of B on C, the torque on gear A was 40. So the torque on gear C has got to be 3 times that. It's got to be 120. But the delta theta is not 2 pi anymore. It's 2 pi over 3 because it's a bigger gear. Multiply them. What do you get? 80 pi joules. 251 approximately joules. What this shows is that there is a conservation of work, in a sense. Whatever work the person put into gear A actually gets transferred to gear C, the same amount of work. 251 joules in, 251 joules out. So even though we have a mechanical advantage where the torque is allowed to be increased, the amount of rotation that the person has to do of that input gear is much more than the rotation that you get out. And so it turns out that work is conserved. We'll show later that this means that energy is conserved. And it is possible in real world gears to have losses in gear systems. In fact, it's a huge part of engineering. Right now, we're just looking at the ideal case, as if there was no friction and no heat losses and no air resistance or anything like that. But later, we'll analyze cases where there are frictional losses.